Today I'd like to show you a strategy to use where you can start with the ideal gas law and determine, given any kind of gas law problem, which of the individual laws you might want to use to solve it. Be it Boyle's law, Charles's law, Avogadro's law, Gay-Lussac's law, or the combined gas law equation. Which one do you use? Well, it just depends on which of those variables are constant. Let's take Boyle's law, for example. And each of these laws I can determine from the ideal gas law, which is what I'd like to do. I'd like to remember just one thing, and then I can derive all the other laws from it. So let's take the ideal gas law. If we have a situation where delta T, or the change in temperature, equals 0, that means there's no change from initial temperature to final temperature, and you're not changing the number of moles, you can take the ideal gas law, state that PV is equal to nRT. That means PV is equal to this, which we said was constant. R is ideal gas law constant. And we said T is constant. So we can express all three of these variables as one constant. And if this is true, we can therefore say P1V1 equals P2V2. That's how I get Boyle's law from the ideal gas law. If I have a problem in which delta T and delta N equals 0. Well, I can do that for the other laws as well. Let's look at Charles's law. We can derive Charles's law from the ideal gas law if we know that if it have a situation in which pressure and the number of moles are constant. If that's the case, we can rearrange and put all the constants on one side of the equation. We say N is constant, R is ideal gas constant, and the change in pressure is constant. Therefore, V over T represents all those constants, which I show here as K2. If that's the case, I can say V1 over T1 equals V2 over T2. Now, by the same analysis, I can derive Avogadro's law with constant pressure and constant temperature. V1 over N1 equals V2 over N2. I can derive Gay-Lussac's law from the ideal gas law equation. That's when volume and number of moles are constant. If that's the case, I just rearrange my ideal gas law equation, put P and T on the left side, and everything on the right is a constant. No change in number of moles, no change in volume. R is a gas constant. Therefore, this P over T equals another constant that I represent K to the fourth. It's 4 prime. And if that's the case, if that equals a constant, then P1 over T1 equals P2 over T2. And lastly, if nothing is changing, then we have from the ideal gas law, PV equals nRT. We have PV over T equals N, which is number of moles. That's going to stay constant. When I say nothing's constant, I mean the pressure, volume, and temperature are all changing in a system. We take our ideal gas law equation, put everything that's constant on the right, represent that as K to the 5 prime. If that's the case, we can use the combined gas law equation. It says P1V1 over T1 equals P2V2 over T2. Now, why did I go through this exercise? Simply to show you that if you just simply keep in mind what the ideal gas law is, based on the situation in which you have different things being held constant or not, you can then use different gas laws. Boyle's law, Charles's law, Avogadro's law, Gay-Lussac's, or the combined gas law can all be obtained from solving and deriving those from the ideal gas law. Now let's do this with a couple examples. Before we do some gas law problems and derive individual equations from the ideal gas law, let's talk about pressure conversion because we need to work in units that are familiar to chemists. Let's take this problem here. During the hurricane formation, as we often see off the coast of Florida, when hurricanes form in the ocean, the pressure is very low over the surface. Let's take an example. If the pressure drops to 745 millimeters of mercury, what is that new pressure in atmospheres? Now, these are probably the two more common units used for chemists in the laboratory. We use mercury barometers to measure atmospheric pressure, and this is an example of here, 745 millimeters of mercury. And in a lot of situations, and especially gas law equations, we want to convert that to pressure in atmospheres. So our process is write down the answer. We want the pressure in atmospheres, write down what we're given, 745, and my unit factor is going to be 1 atmosphere over 760 millimeters of mercury. If this is the case, the millimeters of mercury cancel, and the final answer is 0.980 atmospheres. Now let's look at the gas law problem. Decide which of the gas laws, using my strategy I introduced the first part, to use. Here's a problem. 1.5 liters of methane gas has a pressure of 1650 millimeters of mercury. What is the final pressure if the final volume is 7.00 liters? Well, if this is the case, and I'm not told that temperature is changing, I'm going to assume that temperature is constant. Let's look at from the gas law equation, ideal gas law equation. If my temperature does not change and my number of moles do not change, I can use Boyle's law, P1V1 equals P2V2. This is Boyle's law. So in this example, I rearranged to solve for P2 because I'm asked what's the final pressure if temperature and the number of moles, of course, is constant. I plug these numbers in. I get P2 is equal to P1 times V1 over V2. In this example, P2 is equal 354 millimeters of mercury. Let's take this problem one more step further and convert that to atmospheres of mercury. We do that by not multiplying, but dividing by 760 millimeters of mercury. The millimeters of mercury cancel appropriately. Your answer is in atmospheres, or 0.466 atmospheres. Let's look at my next gas law problem. I have a helium balloon that has a volume of 2.75 liters. If we heat that balloon from 20 degrees Celsius to 40 degrees Celsius, what's the final volume? Here we're told that the change in pressure equals 0. Well, looking at my strategy from the very beginning, I'm starting with my ideal gas law. If I have a situation where the change in pressure equals 0, along with the number of moles, PV equals nRT, I put everything that's constant on the right-hand side, which is number of moles, pressure, and the gas constant. That can represent a new constant equal to V over T. If that's the case, I can use Charles's law. V1 over T1 equals V2 over T2 with constant pressure and constant number of moles. We do this shown here. And let me point out that when you're doing any kind of gas law equation, using any kind of gas law equation, temperature must be converted to Kelvin. So we need to convert Celsius to Kelvin. And we do that by adding 273. So this becomes 20 plus 273, or 293 Kelvin. And this is 313 Kelvin. We rearrange and solve for V2. V2 becomes T2, which is 313, times V1, 275. I'm sorry, that was 275, not 2.75. My initial volume was 275 liters. Back to my equation here. T2 times V1 over T1, 313 Kelvin times 275 liters divided by 293 Kelvin. You see how your units of temperature and Kelvin cancel appropriately. This is going to give me V2 in liters, and my answer is 294 liters. Now we use Charles's law here, and let me just point out once again, anytime you use gas law problems, you have to convert temperatures to Kelvin. In my next gas law problem, I want to look at a situation in which all three properties are changing: pressure, volume, and temperature. Let's calculate the final temperature if we have these changes. Now let me look at my front cover strategy slide. From here, I show that the ideal gas law can be applied to derive the combined gas law, which pressure, volume, and temperature are all changing. Only the number of moles stays constant. I can derive that by putting all the variables I'm interested in and will change on the left, those that are constant on the right, which is number of moles, and of course the ideal gas law constant. And I rearrange that to form a new constant, PV over T, to get P1 V1 over T1 equals P2 V2 T2. So let's use the combined gas law to solve this problem here. We have pressure going from 1 to 2 atmospheres, the volume going from 2.5 to 6.5. What's the change in temperature going to be? Now, once again, we have to make sure we convert temperature to Kelvin. Here's the combined gas law. My T1, of course, I noted here is 25 plus 273 or 298. Now, I want to rearrange this equation and solve for T2, right? Well, just be careful. It's a little tricky algebraically. To isolate T2 on the numerator side, I first want to multiply both sides of the equation by T2, which I've done here. So I get this times T2 equals this. Then to isolate T2 on the left, I want to multiply both sides by T1 and divide both sides by P1V1. So I've rearranged my equation algebraically to get T2 equals P2 V2 times T1 over P1V1. Now we plug in all the variables. We've gotten temperature converted to Kelvin like it should be. And you get T2 is equal to 1,550 Kelvin. Let's look at this final problem. I have a hydrogen gas with a volume of 0.500 liters at STP. Now, just quickly looking at this given set of parameters, I'm not being told that the volume's changing, the pressure's changing from one to another, the temperature's changing from one to another. It's a snapshot in time. What is the number of moles of a gas if it has these conditions, a volume of 0.5 and a temperature at STP? Well, STP means the temperature is 0 degrees Celsius, which is 273 Kelvin, and pressure is 1 atmosphere. How many moles do you have in this particular gas? They're not changing the properties or volume, temperature, and pressure. They're just saying, here's a snapshot of a gas with a certain volume, a certain temperature, and a certain pressure. If it's an ideal gas, let's use the ideal gas law to solve it for N, which is number of moles. And then we're going to make the second step and solve that and convert that to grams using the molar mass of hydrogen gas. So PV equals nRT. We rearrange to solve for the number of moles, which is N, by dividing both sides of this equation by RT. We plug in the numbers here, shown here. Now, remember, when we're using this gas law constant of 0.0821, in these units, we have to have the same units of pressure in the given situation, atmospheres. Volumes must be in liters and temperatures in Kelvin. So everything cancels appropriately. Rearranging and solving for N, we get 1 times 0.5 divided by 0.0821 times 273, divided by 273. If you'll see the units cancel appropriately, atmospheres, liters, Kelvin, this is on the bottom and this is on the top here. So the only thing left is your answer of moles as a number. And when we do that, we get N is equal to 0.223 moles. Now I had a second part of the question. How many grams does that represent? Well, we learned about moles and masses in a previous chapter. If we have 0.0223 moles, we can multiply that by the molar mass of hydrogen gas, H2, which is 1 plus 1, or 2 grams per mole. Moles cancel, and we get units of our grams in our answer. In this case, it's 0.0446.